Welcome to November Papers We Love in San Francisco. Woo! Yay! Yeah, we're almost wrapped up with the year. We have one more. We don't have a location yet, but we will decide it very soon. And then thank you to GitHub for hosting us and for giving us food and drinks. And now we have an announcement from GitHub.
Welcome to GitHub. We're very proud to have Papers We Love here, as always, and we hope to see you again in the future. Yeah, there's food and beverages, as most of you all are aware. A couple announcements. We are hiring, let's see here, machine learning manager, machine learning individual contributors who want to work on applying machine learning to code, machine learning infrastructure and tools. Yeah, there's a theme there. And then folks interested in applying software engineering skills to security, workflow automation, dependency graph work, and a third category of data warehousing. So, yeah.
The machine learning?
Yeah.
Okay, so if you have any machine learning questions, come to this gentleman and ask them.
Yeah, perfect. Awesome. Thank you.
All right, so we're going to get started. If you're unfamiliar with our format, we have a short talk, we call a mini, and then we have a full-length talk. I introduce the speakers with their actual bio and something fake in the middle. So I leave it as an exercise for the listener to figure out which one is real and which one is not. I'm going to introduce Aaron. Aaron Goldman did his graduate work at the Georgia Institute of Technology, where he studied electrical and computer engineering. He has worked on radar systems for the US Department of Defense, anti-abuse at Google, and is currently working in Runtime Application Self Protection at tCell. In his spare time, he's building a new internet out of immutable data. Aaron's recipe for lemon bars has won the Minnesota Country State Fair for 3 years in a row. Let's give it up for Aaron.
See, Minnesota's easy. You wait till I win Alabama, then it'll... All right, today I will be presenting Ideal Hash Trees by Phil Bagwell. I got here when I decided I wanted to try a new language because trying new languages always brings new and interesting kinds of pain into your life. And I decided to choose Clojure because, as everyone knows, Lisp is fun, close parenthesis, close parenthesis, close parenthesis. Clojure has an interesting property. You don't actually change things in this language. You just make a new thing that is slightly different than the one before. And I was very curious when I ran across this of how does this have any performance at all if I am making copies of copies of copies of copies of copies of copies. So I watched some YouTube videos by the founder of this language. The one I recommend to people is that simple is not easy, where Rich Hickey talks about the distinctions there between what makes something simple versus what makes it easy to use, and makes a strong case for we need to make simple software because if our software is too complex to reason about, we will have unreasonable software. And the key data structure at the core of this language is Bagwell's hash mapped array tree, which is in this paper that I am presenting you today. He presents this tree with the main argument that as we have been building hash data structures, we're constantly fighting this trade-off. I can have a really big base and allocate a lot of memory to it, and then I'll have nice short linked lists, and my structure will be fast. Or I can have a very small base, in which case my data structure won't consume a lot of resources in memory, but will gradually get slow over time. So the idea in this solution is that you want to use a trie and say, well, what if our hashes that we're trying to figure out, I'm going to make a really small hash table that's only got, say, in this case, 10 entries in it. And I'm only going to look at the first character of my hash. So now I can put the hashes in there, but I'm going to end up with really long chains. But we have a solution to really long chains of linked lists. Let's use a hash table. So I use this hash table of size 10. And now, as I'm navigating through this, I can go through my root and say, okay, my first thing is 2. So I'll go to the second one. And then I have a 6. So I can go to the next representation, 9, the next one, 4, the next one. And now I've hit a unique place where I'm going it. So as I descend further into the tree, I'm going to have exponentially more of the key space that I'm looking for. The problem with this is when you start implementing this thing, on each layer, you tend to end up with these nodes that are like, I've got 2 things in here. So null pointer, null pointer, null pointer, null pointer, null pointer for null pointer, null pointer, null pointer, null pointer, null pointer. And you end up with these data structures where the vast majority of the space you're using is just in null pointers. But we want this structure of, I have a simple map. So the conclusion is I'm going to, instead of storing all these null pointers, in order to reduce the amount of storage I'm consuming, let's just not store all of the null pointers. So we sit here and we have just a map that says, for each bit in this map, do I have a pointer for this thing or do I not have a pointer for this thing? And then I can point to a new structure that is just the rows that I need. So now I end up with a much simpler data structure where it's going to fit nice and cleanly. Okay. So yeah, the paper proposes that there's 2 kinds of rows in these data structures. Either I can point directly to a key value pair, or I can point to another nested map. We're going to borrow the last few bits because these are pointers and they're word-aligned pointers. There's nothing in the lowest bit. So we can just steal that and say, for my 64 bits, the first 32 bits will be this bitmap that says, which of these pointers do I actually have? And then the second one will be the pointer to the next data structure or the key value. This has an advantage that if I have an empty set, it's now really cheap. I have this one pointer that's on my stack, and it can point directly to a key value pair. And if it's all zeros, this is the empty set. I don't need to stick anything in the heap. If it's one thing, I point directly to the key value pair, and now I have this sort of perfectly efficient first layer of the map because I'm not using any layer of the map. But as I build out, I can say I'm going to point to the base of one of these things and then point to either another subtable or the value or another subtable or the value. So as I keep adding more and more keys, I'm going to end up with more and more of these objects, but it's going to grow with the number of keys that I have and logarithmically with the number of keys that I have. So he then describes this search pattern. I have things in the wrong order. So if I just have these 3 bits, now I can sit here and say, oh, I know that for these 3, the first item here is going to be this first row, the 4th item is this row, and the 10th item is this row. So if you give me a hash to look up, and that hash starts with a 9, I can throw it away right now and just be like, this is not here. In a single 0 bit, I can throw away billions of items in the key space so things fail. You will frequently see for large hash tables that someone will do something like a rainbow table in the front and say, okay, before I even try to look in my data structure to see if this key is there, I want to do something really fast. I'm going to say, is it probabilistically in there? Well, the advantage of this data structure is that your first layer is essentially a rainbow table. Either it's going to tell you, yes, this item might be here, go look in the next table, or no, it's not. And if you're trying to look for things, you're going to run across a large number of failing queries, and these failing queries will fail very fast. Because you just sit there and you're like, oh, this thing's not in here, or this thing may be in here, I'm going to go to the next layer. Now I have another 1 in 32 probability of a false positive, and another 1 in 32 probability. So looking up keys gets exponentially less likely to have failed, or exponentially less likely to continue. It will probably have failed or succeeded very quickly. With certain advantages like, by the time you've gone 7 deep, that's 32 bits of key, and you could have looked up everything in the entire memory space. This entire paper assumes that you have a 32-bit memory space. With a 64-bit memory space, it's a little bit deeper, but not much. You're still bounded. As long as you have a fixed length hash, you're going to have a guaranteed worst time lookup. He then continues to say, okay, so let's say you have this data structure. What is a situation that would be useful to do this for? We could use this to store things in memory, but sometimes we have data structures that don't fit nicely in memory. So how would you build a data structure for a disk that's doing this externalized retrieval? And the answer is, well, exactly the same. I have the first bit that's doing this partition hashing and saying, okay, which drive am I on? And those can map to specific disks. And then within those disks, I just look at a few more bits of my hash that will tell me which sector of that drive I'm in. And then I have a few more bits of hash that will tell me how far through that sector. So simply by navigating through this hash, we get not only a very efficient data structure for here's how you should organize your memory, but a very efficient data structure for how am I going to organize all of my disk. But he decides, why should I stop there? Let's also talk about client-server distributed systems. If I have a really large data set that I can't fit on my own machine, I could have a whole set of machines and say, okay, well, which machine should I talk to? That's just one more layer of indirection. Take a few bits from the top of the hash to tell me which machine. Take a few bits from the top of the hash to tell me which disk on that machine. Take a few bits from the top of the hash to tell me which sector. Or if I have a really big data structure, I could say, okay, which availability zone is this piece of information in? Which rack is it in? Which machine is it in? And as we go to these larger and larger data sets, we can get to data sets that potentially span petabytes or exabytes of data, and the data structure itself doesn't have to change. We don't have to keep sitting here and thinking, okay, what is the right data structure when this thing's in cache? What is the right data structure when this thing is in memory? It's a very efficient data structure if I have the empty set or one thing, so it's a perfectly reasonable structure to use for optionals in your language. A lot of languages have a special case optional type. Is this a thing or is this not a thing? You could use one of these trees. It either points to the thing or it doesn't point to the thing. It's cheap. Or you could use it for, this is the DNS root of the internet and has every domain name in it, and it's still going to scale linearly. So he goes through, how are you going to do this bucket search? How are you going to insert things into this? If you overfill a partition and you go to that name, he suggests you just spill over to the node next to it and then update your tables for where the slices are. So if I want to update one of these things, I can use a hash, but hashes are going to cost me this randomness. But because this is such a dense data structure, what if I just don't hash my keys? Now I can stick everything in directly order. So these are the vectors that you see in Clojure. As you start building up a vector, if you have one thing, you're going to point directly from your stack onto the object. As you start filling this up, eventually you're going to put to the point where you have a 30-second thing that isn't going to fit with one layer of indirection, but I can just repoint my root at this new node, and now it points here, and I point one thing to the next one, and I just make these new objects repoint my root, and all of the old objects still exist. So if, say, there's another variable that is, question? It is a B tree. The main distinction here is that it is not keeping track of all the nodes. It is a very wide B tree because it's 31 as opposed to being a straight binary B tree that is going either way. As well as if you have a sparse data structure where you have a lot of zeros in it, you get this real benefit at the top that I have a map to go through. So I'm not actually going to store all of these null pointers that are going to end up taking up a lot of space. Does that answer the question, or?
I have a quibble going forward, but I'll just leave it.
All right, I will talk to you after. So he then proposes, like, how should you use these things? If you have an IP routing table, you can relatively cheaply make one big base that's going to store all of the first directs, and now know with only one pointer chase, I can get all of these things into memory. And that if I have a class system, again, this is something that I feel leads to the use in a programming language. I can have a whole bunch of named classes in a highly dynamic language like Clojure, and that's fine because it's just a dictionary. The global space is just a dictionary that's got a bunch of namespaces in it that are just dictionaries that have a bunch of variables in it that are either pure values like ints or more dictionaries that are my objects with fields in them. And we get the same data structure is useful, again, in different places. So then he talks about performance. We can force it to be constant time by saying, I'm going to do my max depth. one of the criticisms of this data structure has been, well, you're not actually a hash table because you're logarithmic, and a hash table must be constant time. So he goes through his examples and says, well, we can size the base dynamically and say, as the number of things we have grow, then we're going to resize the base, and it's going to look like a traditional resizing hash table. And that will give us our sort of hard-coded, constant time version of this. Or we can have the logarithmic version, where we say, okay, I'm just going to have a single 64-bit int that is my stack reference to something, and then on the heap have these small fixed size structures. Or I can have a traditional hash k size 2k, 64k, 512k. And you can see that we actually get performance that is pretty close to the ideal performance that we're going to get with a traditional hash table, even though we have more of these things, because we are actually on a system that has non-uniform memory access. Yes, it's true that you're going to be reading the root of the table a lot of times, but it's only going to be expensive the first time. After that, it's just going to be in cache, and the parts of the data that you're looking for are going to be in cache. So if I want to do something like iterate over all of my keys, I'm not going to have to keep going through and looking up the first and second layer and first and second layer and first and second layer and first and second layer, because that's going to be in my local and most heated cache. Inserting having similarly comparable times. So this is something that it's fast to insert into because we are just descending into this logarithmic data structure. It's fast to read from because we're descending into this logarithmic data structure, and we don't get into the pain. We've looked in previous papers at this conference about a whole bunch of different, how are we going to design these hash tables and chasing pointers, and if something's out of the way, can we move it, and do we look for the first free spot or rob from the rich and get, like, there's a lot of complexity you can do to get your hash tables to be both fast and dense. This is a very straightforward structure for doing that, and it gives you this additional power, which Bagwell doesn't actually reference in the paper, but is one of the strongest things here of you can simply make new nodes without abandoning the old nodes and get very efficient structural sharing. If I'm building up data sets by adding keys and adding keys and adding keys, and someone says, okay, I would like to take a snapshot of that at some moment in time, the thing that I gave them was a 64-bit integer. And they now have a pointer to a arbitrarily deep tree, whether that is an optional that has one thing in it that they're grabbing at a moment in time, and even if you change what's in there later, they're still holding their reference to the tree, or if it's some deeply nested structure that is spread across multiple data centers and multiple racks and multiple machines. It's very difficult to take a checkpoint of a data structure that is that large, but if I build something that's truly immutable, then, you know, I like to say that immutability is cheating. There's a lot of really hard problems in computer science, and by going through this system, we can say, you can just cache things, and you can just snapshot things, and we are relying on the garbage collector to collect these objects, but because they're all fixed size, there's only 32 sizes here. It's 1 row to 32 rows. As you need new objects, you're going to have things on the free list that pretty much match the sizes you want. And you're going to pay significantly less than double the size of your data. So you get an efficient data structure, and if you're going to be making copies, I assume that someone here has written deep copy at some point on some data structure because they were working on a distributed system. Anyone? So you start looking at these things and you say, okay, what is the real cost of immutability? And the answer is, well, you have to keep the old things around because duh, plus a much less than half the size. So if you are willing to do deep copies that is going to double it, by the time you have done a second deep copy, you probably would have been better off just using an immutable data structure in a hash map array tree. So my final conclusions of this paper, they are both fast to look up keys that exist. They are fast to look up keys that don't exist. They are fast to insert new keys if you're trying to update a key that exists, and they're fast to insert keys if they don't exist. If you decide that you don't want to hash the values, and instead of having a very nice uniform thing, you get things in order, this is going to let you do a lot of the range queries that you want, because there are many applications where you really want to do querying of keys over ranges. You're not going to get quite the density because you are going to have deeper chains as you have longer chains of matching at the beginning of your keys. But that doesn't tend to be a problem if you're implementing something like, say, an array, where the keys are the numbers from 0 to infinity, and you add them one at a time in order. That becomes a very efficient structure of this. And that if you are in a garbage collected system, this becomes a very efficient way to use that system, because GC is pretty good at freeing and reusing objects that are all going to be the same size over and over again. And my final thoughts are, I think that this is an interesting data structure, but Bagwell didn't take it quite far enough. In my personal opinion, we have built an entire internet that's basically built on mutability. If I send you a link, there is a link up here. It goes to these slides. Right now, if I decide to change what that link goes to, I can repoint that link at something else. I can take that link away in the future. If we want to build robust systems at internet scale, I think it makes sense for us to start having very large persistent data structures that we use to reference things from one place to another. Questions? How much time do I have for questions? I think I'm a little over already.
No, it's fine. Any questions?
Just to follow up on your very last point, do you see anything that exists already in terms of this like internet that we've built that is more immutable?
So there are projects like IPFS, and there's a named Bitcoin thing that's trying to use that as a immutable store. And we have some old projects that have been trying to do similar things for a while, like Freenet, whose whole idea was the only name that anything has is its hash, and you throw it in, but those tended to not scale well. I think that there is a lot to be said for a much simpler structure of immutable data. That if I have my root and you have your root and I point to you, you may update and re-sign your key, but my link is to a moment in time. And that's not something that I've seen really adopted on a internet scale, and it's certainly not something I have seen in any kind of internet standards.
More questions? Do you want a mic or not?
No, I'm good.
Okay.
Yeah, so Git
IDs are more or less representing one of these keys.
Git IDs are similar. You have some interesting problems with submodules. Git can get a little cranky at you if you have multiple repos that each have each other as a submodule.
Yeah, I wasn't saying that Git would be the implementation. I'm saying that the concept.
But yeah, I very much like the concept of Git. If I were implementing an immutable file system, yeah, you want to have, these are my blobs of data, and here are lists of those blobs, just like the Git trees, and everything rolls up to a commit. Sign that commit object, and if you have a new commit object, you can recognize it because it's signed, and that's a very inspirational structure. I feel like we could do a little bit more with the I want to reference another signed commit object in another repo, and have more meaningful semantics around, do I want to follow this to the thing that's actually there, or do I want to follow this to the thing that was there at the time it was referenced? And I think we could use some better semantics around what is referencing something exactly versus getting the most up-to-date version of the thing that was referenced because it's being signed. But that's true. Git is probably the most successful immutable data store currently.
No? So you're looking at me? No? All right. Thank you so much, Aaron.
Thank you.
We're getting ready to announce next year's lineup. I think I'm booked until March, but I don't have minis. So if you're interested in giving a mini, let me know. Now it's time for our main talk. Let's tell you a little bit more about David right now. David is a software engineer from David is a software engineer from Sydney, and he's actually traveled from Sydney today. He currently works for Heptio, building tools to improve the Kubernetes experience for everyone. David spends most of his free time contributing to the Go language project by writing, speaking at, and organizing Go-related events. In his spare time, David likes to train his dog Kubernando to reenact scenes from Magnum PI. Let's give it up for David.
Holy shit. Cool. Thank you very much for coming to hear me speak tonight. Especially, it's wonderful to see friends in the audience who are here not to see me talk about Go. So it's a distinctly unnerving privilege to address you tonight. Like kind of like the radio saying, like long-time listener, first-time caller. Like PapersWeLove is this wonderfully whimsical and crucially important endeavor. I think especially in our field, which has a bit of a tendency to ignore even the recent past. So I want to thank you, Ines, for accepting my proposal, and GitHub for hosting us tonight, and also my employer Heptio for letting me turn what was supposed to be a stopover into a week in San Francisco. So the paper I've chosen tonight is a retrospective on a computer design. It's one of a series of papers by Gordon Bell and various authors spanning the design, the growth, and the eventual replacement of the company's iconic line of PDP-11 mini computers. I think it's fitting that 2007 represents the 60th anniversary of the founding of the company that produced the PDP. And it's also 40 years since this paper was written. So I thought that it might be entertaining to look back on Bell's retrospective with kind of the wisdom of the lens of our own hindsight. And the PDP also has this kind of recurring personal connection from me. This is me, I think probably 4. I talked to my dad about it, we're not quite sure. Playing Adventure on a PDP-11 over an acoustic coupler back in the early 80s. So to set the scene for this paper, first we should talk about the company that produced the PDP-11. That is the Digital Equipment Corporation of Maynard in Massachusetts. And they're better known to most people as DEC. DEC was founded in 1957 by Ken Olsen, pictured, and Harlan Anderson. And Olsen and Anderson had worked together at MIT's Lincoln Laboratory, where they'd noticed that the students would queue up for hours to use this computer called the TX0, which was an experimental interactive computer built by a guy called Wes Clark. So this is the TXO. What do you notice about it? Like, just yell out something that seems odd or strange. It fits in one room. That's good. Yeah. One other guess. One terminal. Yeah, and especially, I'm pretty sure that's a screen. So let's compare this to something like the IBM 704, which was the contemporary mainframe of the time. And this is the mainframe that the MIT students were ignoring to line up to play with the TXO. So what Olsen and Anderson kind of recognized was that there was this desire for interactive computing. And perhaps it was so strong that there was a market for small computers dedicated to this role. And so DEC's first offering was the PDP-1, which was effectively a commercialized version of Clark's TX0. And you can probably see some similarities between the previous photo. And it's also worth noting that the PDP is an acronym for Programmed Data Processor, as at the time computers had this reputation for being big, complicated, expensive, and DEC's venture capitalists said that they wouldn't support them if they called it a computer. So they called it something else. And following on the success of the PDP-1, DEC's offerings blossomed into several families of computers, many of which were designed, at least in part, by Gordon Bell, who's the author of tonight's paper. Okay. So a computer is not solely determined by its architecture. It reflects the technological, economic, and human aspects of the environment in which it was designed and built. The finished computer is a product, therefore, of the total design environment. And I love this opening because right from the beginning, Bell is letting us know that the success of any computer project is not just abstractly building, like, quote unquote, the best computer. It's building the right computer. And that's a matter of context. In this chapter, we reflect on the PDP-11, its goals, its architecture, its various implementations, and the people that designed it. By this time, this was 1976, Bell had been the VP of engineering at DEC for nearly 4 years. It's clear that he was considering the success of the PDP-11, like in this wider context of the market which it was built to serve, and ultimately which would later influence the evolution of the PDP itself. So, in keeping with the spirit of Bell's words, tonight I'm just going to focus on two aspects of the paper: the technology and the people. So Bell opens with this observation: it's the nature of computer engineering to be goal-oriented, with pressure to produce deliverable products. It's therefore a little bit difficult to plan for an extensive lifetime. And what struck me here is right here, this is your Agile mindset. This is 25 years before Snowbird, before the Agile Manifesto. Like, Bell is talking about the pressure to produce what we call a minimum viable product, and how that just tramples over your desire to plan elaborately. So when this was written, DEC weren't a startup either. Like, they weren't a company looking to make their bones. They've been in business for 20 years. They had several established product lines under their belt. Now, like the IBM 360, the PDP-11 was designed not just as a single model of computer, but it was a range of models, for which software for the small ones would work equally well when you upgraded to the big one. And because of the open nature of the PDP-11, anything which interpreted the instructions according to the processor specification was, by definition, a PDP-11. And there'd been a rush within DEC, once they realized that, hey, this PDP business could be a thing, to build different implementations. You had different groups within the company going after different parts of the market, building fast, expensive ones, and others building slower, cost-reduced versions. So, Bell goes on to say, despite its evolutionary planning, the PDP has been quite successful in the marketplace. It's not clear how rigorous a test, aside from this marketplace, we've given the design, since a large and aggressive marketing organisation, armed with software to correct architectural inconsistencies, can save almost any design. And this is, so Bell is introducing his hypothesis. Was the PDP really a great design, or was it simply the beneficiary of a hyperactive marketing department? And at this point, Bell begins to reflect on the product that emerged and evaluate it against their design goals that they'd set in stone about 6 or 7 years ago. The first weakness of mini-computers, Bell writes, was the limited addressing capability. The biggest and most common mistake that can be made in any computer design is not providing enough address bits for memory addressing and management. So mini-computers of that era often came with a 12-bit address space, 4,096 words of memory. It's worth taking an aside to just note that the word mini-computer, which has later come to be understood as like an indication of size, like small, actually originated as a contraction of the words minimal computer. The canonical example was the PDP-8, which was DEC's previous offering and offered a sum total of 8 instructions. The reason for this tiny address space was cost. Memory was extraordinarily expensive in the 60s and 70s, as each bit consisted of a tiny little iron donut woven onto metal control wires. Cores, as they were known, were arranged in planes, and in this case representing 4,096 bits, and those planes would be stacked one on top of another to make a word. So a 4,096 word memory had 16 million iron cores, all of which were at least partly hand-assembled. So you can see why memory was expensive. Bell and the other PDP-11 designers knew that the cost of memory was going down, and that semiconductor memory, which was at the time, like late 60s, was not cost-effective yet, but they could see in the future it would continue to drive down the price per bit. Thus, Bell wrote that the amount of memory that customers could afford to buy would increase over time because, as he called it, this kind of constant dollar effect. They would spend the same money and next year be able to buy more memory for the same money. But unfortunately, the PDP-11 followed the this hallowed tradition of skimping on address bits, and was saved by the principle that a good design can evolve through at least one change. So even with that foresight, Bell noted that not 2 years after the introduction of the PDP-11, it had to be redesigned to include memory management to allow them to have a larger 18-bit address space. And apart from the cost and work and redesign of this represented a programming complexity. Now it was harder to program the machine. A few years later, they had to add a further 4 bits. Now, in fairness to Bell, I mean, he's chastising himself here for not seeing this coming. But this pattern of insufficient address bits continues today. Like, who's ever fought with the DOS 640K limit? Who's ever had to reconfigure their high-mem.sys? Who's struggled with a 32-bit program that needs more than a 2 gig heap? Exactly. So, as you pointed out, none of us are perfect. The second weakness of minicomputers was their tendency to not have enough registers. This was corrected in the PDP-11 by providing 8 16-bit registers. And it was not uncommon, even for mainframes of the day, to only offer a single register, the accumulator, where all the results would be accumulated. If you were lucky enough to have additional registers, and these were very expensive because they were extremely fast, they would be provided for special purpose use, like indexing or address operations. What I like about this is there's a quote at the bottom that says, more registers would increase the multi-programming context switch, which is obvious, there's more to save, and confuse the user. My interpretation of that, in the early 1970s, the assumption was still that the machine would be mostly programmed in assembly, and so having more registers would be harder for the assembly programmer to figure out how to use. Now, there's a strong interplay between the number of registers you have in the architecture, the number of address bits you have, and the size of the instruction word. All these factors are rooted in the scarcity of memory. So I think it's worth taking just a little detour to talk about instruction set design. In von Neumann machines, of which almost all of them in the 60s were, the program and its data share the same address space. And therefore, that address space is limited because you have to share. So inefficient programs didn't just waste memory or computing. They didn't just waste computing time, they wasted memory as well. A slow program, was somewhat tolerable, but a program that was too big to fit in memory because it was inefficiently written was a fatal condition. So you want your instruction encoding to be as efficient as possible. And as an example, let's consider the common case of moving a value from one address in memory to another. How many bits would it take to describe that operation? So one potential implementation would be this. We'd have 16 bits for the source address, 16 bits for the destination, and we need a few bits at least to describe the operation we want to do with these two. So let's call that 40 bits. 40 bits isn't an equal multiple of 16, so it means your instruction word is this kind of weird 2.5 kind of word instruction encoding. It's pretty bad. But what if we were able to load those values into a register? Then you'd only need to describe the register, in which case the PDP has 8 registers, so we need 3 bits, and then 3 bits for the destination, and then again some for the operation you want to do on those, but you can see this easily fits in less than 16 bits. Now it actually turns out that the PDP-11 uses 6 bits per operation. 6 bits per register, and we'll go into why that is a little bit in the future. But even with 6 bits per source and destination, you still have 4 left over for the operation. And that gives you a very compact instruction encoding. So Bell continues that the third weakness of minicomputers was their lack of a hardware stack capability. And in the PDP, this was solved with the auto increment, auto decrement addressing mechanism. That's what some of those bits went for. The design of the PDP-11, now, it's hard to imagine hardware these days that doesn't have the notion of a stack. Like, that seems improbable. But consider the stack isn't as important if you don't need to support recursion. The design of the PDP-11 was laid down around about 1969. And if we look at the programming languages in use at the time, it was predominantly Fortran and COBOL. And neither of those supported recursive function calls. So the function call sequence in the hardware that came before the PDP would often store the return address at the address you just jumped to. This made recursion impossible. The PDP defined what we now know as a stack pointer, and as we understand today, as just a register that controlled the operation of like push and pop style instructions. But it went one better and permitted any register to act as a stack pointer by the addition of these auto increment and decrement instructions. So to give an example, this is a single instruction. It will decrement the value stored in R6 and then move the value stored in R4 into the address stored in R6. So this is how you push a value onto the stack in the PDP-11. And if there are any ARM programmers in the room, this might look quite familiar. This means you don't need a dedicated instruction for push and pop, like you have in other processors that had a dedicated stack pointer. They would have to dedicate some of their instruction encoding space to actually having push and pop. And it allowed any register to be the stack pointer. You could have multiple stacks at the same time, and this was quite frequent. Although traditionally R6 was the hardware pointer you would use if you were doing like a jump, a call and return type instruction. The fourth weakness, and Bell's talking about existing mini-computers in 1969, was limited interrupt capability and slow context switching. And this was effectively solved in the PDP-11 with the ability for devices that raised an interrupt to actually give the address of the interrupt handler. And why is this important? Well, at that point in DEC's lifetime, almost all of its products, save the PDP-10, which was their big mainframe offering, were aimed at interactive laboratory or process control type things. So these were what we would call today real-time computers. So interrupt responsiveness, the delay between the signal being raised and the computer being ready to actually do something about it, is super important in real-time programming. And the way that the PDP addressed this was by permitting the device that raised the interrupt to supply the address to go to. And so Bell reported quite proudly that this basic mechanism is very fast. It requires only 4 memory cycles from the time the interrupt is raised until the first instruction of the actual interrupt routine begins. Now, string and character handling were of increasing importance during the 1960s, as you had these fields of scientific and business computing kind of converging. The predominant character encoding at the time were these 6-bit character sets, which have just enough space for all the English letters, the numbers 0 to 9, and a few punctuation characters, which are pretty much all you can do to print out financial reports. And again, this comes back to memory. Because memory was so expensive, placing one 6-bit character in like a 12-bit or 18-bit word was criminally wasteful. And so those characters would be packed together into words, 2 or 3 to a word, sometimes more. So this provided for efficient storage, but it was really complex for operations like move or search or concatenate, because you had to account for the fact that the character could be at the top or the bottom or the middle of the word as you're trying to copy and move them. And so while this was efficient kind of encoding space to pack the characters in, it was inefficient because you had to code a lot more to deal with these edge cases of the character being at the top or the bottom of the word. So the problem was addressed in the PDP-11 by allowing the machine to operate on memory both as a 16-bit word and as what was at the time the increasingly popular 8-bit byte. So the expenditure of these 2 bits was felt worth it because of the simpler string handling. And it also eased the adoption of the increasingly popular 7-bit ASCII standard, which DEC were big proponents of at the time. And Bell concludes this point with this somewhat throwaway line. Although string instructions are not yet provided by the hardware, common string instructions like move, compare, concatenate can be programmed in very short loops. And indeed they can. You can write a string copy routine using just 2 instructions, assuming, of course, that the source and the destination you've already loaded into registers. And this is what it looks like. And this takes full advantage of the fact that the move instruction operates the processor flag. So as it's moving bytes from source to destination and then updating the addresses stored in the registers, it's checking to see, is the source 0 each time? And if it isn't, it drops through the loop. And this is fundamentally why C strings are terminated by zeros, because it was really cheap to do. The 6th weakness was the inability to use read-only memories. And this was avoided in the PDP-11. In process control applications, which was really where DEC had made its name, where the program is relatively fixed, like you might lose power, you might need to restart the machine, but you're always going to load the same program. So at the time, you would have to maintain, like you'd have to have a tape reader or like a punch tape, paper tape reader or something like that to load in this program every time you needed to restart the machine. And this was expensive, like you had to buy it and you had to maintain it, even for the infrequent times when you need to restart the machine. It would have been far more convenient if you could just have the program always present in the computer when it started up. But because of the extreme memory shortage of early mini-computers and the lack of notation of like any kind of stack, people were forced to write self-modifying code, and you can't have self-modifying code in a ROM. So through the design of the PDP-11, Bell is justifiably proud that they just kicked this one out of the park. Like, they could use ROMs whenever they liked. They used them heavily throughout. That you would have diagnostic boards that you would plug in that had basically a diagnostic program on it. You wouldn't ship like a diagnostic disk. You'd literally just come along with a piece of hardware, plug it in, and it would do the diagnostics. Now, Bell's 7th criteria is I/O capabilities. During the late 60s, when the PDP was being designed, input-output, probably like everything else, was very expensive. Like, mainframes at the time used a model called channel I/O, where the main CPU would send a little program to basically another computer to ask it to do the I/O on its behalf. The program would usually instruct the tape drive controller to go and search on the tape for a particular record and then go and load it, or maybe tell the card punch to punch out a whole card. Now, channel I/O was important because it allowed the mainframe to basically offload that work to another CPU. And this was very important because mainframe cycles are very expensive. So if you can make the I/O operation happen somewhere else over there, you can go back to doing paid work. It also permitted overlapping I/O. You could have multiple channels doing multiple things. And this meant that the utilization, because the mainframe CPU wasn't doing the work itself, kind of went up. Now, the downside of this is that, like, as I've said a few times, there's another smaller computer. In fact, several smaller computers connected to your mainframe. And this drove the cost up astronomically. This was one of the key underpinnings of why mainframe computing was so expensive. Now, over in the mini-computer world, I/O was usually performed directly by the CPU. And this usually took the form, this is from the PDP-8, of specialized instructions, hard-coded to do exactly one thing. They know there is one punch attached to the computer, and there's an instruction literally for go and punch this character. And then you wait until that punch is done, and then you go and punch another one. So it's very laborious, and it's also hard-coded. Can't have 2 punches. Can't have a new kind of device. So the PDP introduced something unique, which is called in their documentation memory mapped I/O. And this isn't the memory mapped I/O that like we probably think about now. Like this isn't mmap2. This is just the convention that a specific address in memory isn't just like a cell of memory. It's actually routed through to the backplane, to a card sitting in that backplane to control something that it does, just by reading or writing an address. For an example, the value written to 77566 would actually cause that character to be written out on the console, which was usually a teleprinter or a hard copy printer. If you read the value at address 77570, you would get the value entered on the console switches. And this was all used as an early form of bootstrap configuration. You would set the amount of memory or which device to read from or write from to customize a small program that had been loaded into memory. Similarly, if you wanted to talk to the disk drive, this was accompanied by writing the sector you wanted to address 77412, the address in memory you wanted it transferred to another register, the number of words to a third register, and then finally by setting the bottommost bit, you can see on this picture called go, of address 77404 to 1, that was a signal for the drive to go find that sector, read it into memory and transfer it directly into memory without having to, without much coordination with the CPU. You could ask it later on to send you an interrupt when it was done, but that was all the kind of care and feeding that it needed. My favorite one has got to be the PWL11 line clock. If you write to bit 6 of address 77546, it starts an interrupt firing every 20 milliseconds. What's so special about 20 milliseconds? If I told you that in PAL regions it would be 16.6 milliseconds, yes, it is. That's exactly right. It's the reciprocal of the AC waveform. So just like your bedside clock, the PDP told time by counting power line cycles. That is brilliant. So the final and ninth weakness of minicomputers was the high cost of programming them. Bell writes that many user programs in assembly language without comfortable environments of editors, file systems, debuggers that were available on larger systems. Because their minimal nature, minicomputers weren't necessarily the most pleasant environments to program on. Sometimes it involved a lot of switch flipping, as we saw with the MITS Altair, that was programmed entirely by flipping switches. Or perhaps you had to edit your program somewhere else, produce a tape, maybe move that tape to another, and then finally load it into your computer. And I think of this as very much akin to like if you work with microcontrollers today. Like you will compile a program on your workstation, you'll produce a hash, like a hex file, and then you'll have to like burn that hex file onto your microcontroller. But it seems that Bell was either unaware or not really interested in the work that Thompson and Ritchie were doing on their PDP-11, building, as they say later on, their own programming environment on their PDP-11 down there in New Jersey. So now we can move on to the second section and talk about the people. And as an amateur historian, and I caution you that I do use these words extremely loosely, this section is the most interesting to me because the study of the history of computing, or really like any study of history, is fundamentally about the study of the people and the context surrounding the decisions that they've made. So Bell recognized that while computers are built from technology, they're built by people, and so he dedicated this entire section to the paper of talking about the group dynamics at DEC during the development of the PDP-11. I found this the most fascinating part. So Bell writes that problems faced by computer designers can usually be attributed to one of two causes: inexperience or second systemitis. And so Bell is recalling the words written by Fred Brooks from his recent, this is 1976, it was only published a year before, book at the time, The Mythical Man Month. Brooks had been the lead for the OS 360 project for years and had struggled to build a general purpose operating system that would work across the entire range of IBM's 360 models. This was, of course, the goal of the 360 to have software compatibility from the smallest and slowest to the largest and most powerful. And so I think that Brooks's words must have been fresh in Bell's mind when he was writing this paragraph. I love this. This section is a perfect window into the operation of DEC in the late 1970s. The internal organisation of DEC's design groups has through the years oscillated between market orientation and product orientation. Since the company has grown at a rate of 30 to 40% a year, there's been a consistent need for reorganisation. And at any given time, 1/3 of the staff has been with the company for less than a year. I don't know, raise your hand if this sounds familiar to where you work. At the time of the PDP-11 design, the company was structured along product lines. And for the next fair while, Bell spends some time iterating through each of the groups and listing their strengths and weaknesses as potential sponsors for the PDP-11. Now, in the interest of time, I won't recount all the choices, but I do want to mention this one exception. The PDP-10 group was the strongest group in the company. They built large, powerful time-shared machines. They're essentially a separate division of the company, and they had little or no interaction with other groups. And although the PDP group as a whole had the best understanding of system architecture, they had no notion of system range. They were only interested in building the highest performance computers. And having recently worked for a software company where one or two of the oldest products made all the money, I have some sympathy for Bell's position. The PDP-10 was DEC's version of a mainframe. It was enormously powerful, but it was only available at one price point, the biggest. The first design work for the 16-bit computer was carried out under the eye of the PDP-15 manager. This was a person with marketing person with an engineering background. The first design was called PDP-X and included a specification for a range of machines. Unfortunately, the group managed to convince management that their design was potentially as complex as the PDP-10, which Bell thinks it wasn't, and thus ensured their design because nobody wanted another large computer unrelated to the company's main large computer business. I think the lesson that Bell's teaching us here is quite important. When your competition is in the same line of reporting, they have some fairly effective tools to make sure your product never makes it to market. And this little bit of shade down here might go unnoticed by the casual reader. In retrospect, the people involved in the design of the PDP-X were apparently working simultaneously on the design of Data General. But I think that this is a reference to the defection to rival like that of the Shockleys Traitorous 8 a decade earlier. Pardon me? Yes. So, Edson DeCastro, who was the product manager of the PDP-8 and was lead on the PDP-X project, had left DEC, and he'd taken several of his team with him, and they'd formed a new company called Data General. Now, the record, at least to me, is not clear whether DeCastro left because the PDP-X was cancelled, or if his departure was the final straw that basically killed the project. But in either case, the results are basically the same. As the PDP-X project folded, the desk calculator machine, and where Bell says a name chosen for security, and I think he means to hide it from the PDP-10 group, was started. The design and planning were in disarray as Data General had formed and were competing with the PDP-8. So Data General were now competing with DEC with a 16-bit mini computer in the space the PDP-8 had defined, and Edson DeCastro, who was the product manager of that, knew like the back of his hand. Rack-mounted laboratory equipment. I mean, just to make this very clear, this is the PDP-8. It fits in a 19-inch rack. It's designed for process control. And this is the 16-bit Nova. This is what they left and started competing with. So the last section of the paper, having evaluated the PDP against its predecessors, Bell spends some time evaluating the 11 against itself, against its own design. And the biggest takeaway from this section is the Unibus. As Bell writes, in general, the Unibus behaved beyond all expectations. Several hundred types of memories and peripherals, so several hundred types of cards, accessories, have been interfaced to it. And it's become the standard architectural component for systems from like $3,000 to $100,000. So, what's a unibus? In the earliest commercial computers, like going back to the 50s, they were designed with these kind of plug-in modules. This is from a 700 series IBM. And they were designed with these kind of logic components because they had to be easy to service. Like these things were incredibly unreliable. So rather than like fixing or debugging it in situ, you would just rip the whole module out, replace it with a spare, and then go and fix it on your own time. A little bit later, the desire to build computers out of standardized logic modules came along. This is actually one of DEC's early product offerings. They didn't just do computers, they actually had just sold raw logic boards. And this probably has 2 or 3 logic elements on it. And you would take these as kind of standardized building blocks, and you would connect them into a backplane and wire that together very elaborately to produce a computer. So you can see a whole stack of them here. This is the backplane of a PDP-8. Like each of those cards is what we just saw on the previous slide. So the unibus represented an evolution of this previous design. And it's more like an abstraction of an idealized backplane. Like rather than having to actually physically wire it, you can just have one simple backplane that connects everything with a common protocol. And this was made possible by the availability of like slightly better integrated components, what the literature calls medium scale integration. And this moved the complexity from the backplane into the cards that plugged into it. And this permitted the decoupled design that is the unibus. It was a standard bus for plugging cards into. And this design is with us to today. Like I think anyone who's built or maintained a desktop computer like knows what I mean when I say a backplane, a bus, a bunch of slots in the back of your computer, where the interface is literally, it fits in that socket. It follows that standard electrical protocol. So the unibus as a standard has provided an architectural component for easily configuring systems. And when he says configuring, he's talking about configuring for sale. Like a customer would want a computer to do medical research or to do some kind of process control. So that's what he means by configuring. Any company, not just DEC, can easily build components that interface with this bus. I mean, prior to the unibus, IO devices in mini computers could only support the ones that they were programmed to do. Like as we saw the previous example, you needed an instruction that said read from the paper tape and one that said punch a character. It was almost encoded into the CPU logic. After the unibus, the field of end-user customization and experimentation was like just cracked wide open. So what have we learned from the PDP-11? Now, Bell's retrospective ended when this paper was written in 1977, but from our vantage point, 40 years later, at least to me, the impact of the PDP-11 has been enormous. First of all, while the PDP wasn't designed or even really understood to be a RISC processor, I mean, that term would not be coined until 1976 by John Koch. If anyone has any experience with like ARM processors, which is a fairly contemporary RISC microprocessor, the similarities between the instruction sets are striking. So just like programming language design is a process of evolution and cultural poaching, it seems that so is instruction set design. And the PDP also drove this stake straight through the heart of dedicated I/O instructions. It cemented this model of memory mapped I/O for control. And this is absolutely the predominant mechanism that we use today. The only processors that I can think of post the PDP-11 that had dedicated I/O instructions were the Intel 8080 and its Z80 clones. Since then, I can't think of a microprocessor that has treated I/O separately from memory access. Next is the PDP's impact on software and operating systems. The PDP is the 11 is the machine that Kem Thompson and Dennis Ritchie developed Unix on at Bell Labs. Like before the PDP-11, there was no Unix. Before the PDP-11, there was no C. This is the machine that C was developed on. If you want to know why the classical C int is 16 bits wide, it's because of the PDP-11. And Unix brought us ideas such as pipes, everything as a file, and this idea of interactive computing, the shell. In interactive computing, memory usage is effectively unbounded. And while the PDP was perfect for process control applications, this demand for interactive computing was the hallmark and the driver for its replacement. The year this paper was released, 1977, was also the year that the PDP-11 successor, the VAX, was introduced. Now, VAX stands for Virtual Address Extension. So you can see that Bell is not going to make the address-based mistake again. Unix had also arrived in Berkeley by 1974, aboard a tape carried by Ken Thompson when he went on sabbatical there. And it's going to evolve into this West Coast-flavored Berkeley system distribution, which is closely identified with Bill Joy. Unix had been ported to the VAX by the start of the 1980s and was thriving as this countercultural alternative to DEC's own VMS operating system. Berkeley Unix spawned this new generation of hackers who would go on to form companies like Sun Microsystems, the language Self, which itself led directly to Java. Unix was ported to this bewildering array of machines in the 80s. And after the kind of fallout from the Unix wars, we were left with the various BSDs that we know them today. 4BSD, a descendant of the original Berkeley distribution, became the basis of the operating system for Steve Jobs' NeXT. And so when Apple purchased NeXT in 1997, NeXTSTEP and its BSD-derived user space became the foundation for Darwin and OS X and iOS. Now, we saw earlier with Edson de Castro that DEC were no stranger to breakups. Dave Cutler, the architect of the VAX's VMS operating system, after a failed attempt to start a new kind of combined operating system hardware project, which was designed to succeed the VAX, decamped to Microsoft in 1988 and bringing with him most of his team, who went on to develop Windows NT. And to close the loop on the de Castro story, the Data General Nova series provided the inspiration for Charles Thacker and Butler Lamson's Alto. And the Alto itself is the fabled inspiration for the look and feel for the Apple Macintosh. And the rivalry between Data General and DEC continued into the 32-bit era, and this story is told in Tracy Kidder's Pulitzer Prize-winning 1981 novel, The Soul of a New Machine. So what have we learned from the PDP-11? I think while its development was certainly chaotic, and it's certainly not without its flaws, the PDP is at this nexus of so many threads of history. Hardware, software, programming languages, operating systems, all of these you can trace back, at least indirectly, to the PDP-11. I'm going to wager that there isn't a single person in this room who can't trace the lineage of the language they work with, the computer they use, or the operating system it runs, back to the PDP-11. And I think that that's incredibly unique and notable. So thank you very much for your time. Questions?
All right, questions?
Bearing in mind that I was born in '76 and this computer predates me by about a decade, but please ask anyway.
All right.
Just yell it out, sir. I'll repeat it.
Do you know what the incentive was for them to add a hardware stack? Were they trying to support other languages that was?
Wait. Go to Garrett.
Do you know what the incentive was for them to implement a hardware stack? Were they trying to implement other languages that where they needed that?
Do you want to go first, sir? Or?
Really talk about the hardware stack. You have auto increment and auto decrement addressing. Sure.
Yeah.
And the stack more or less fell out as a convention. So there wasn't really you could impose just by doing a jump through an auto increment. Say return to that. But the call instruction just use that. You didn't even have to do the same. There wasn't an identified stack pointer. That was a convention to use R6. The program counter was also a register. And so the reason things were positioning dependent was because you could add an offset to a register to form an address. And so the compiler would generate find me the location, 2,000 words from the current program counter.
Yep. Yep.
Do you want to repeat it?
So,
Fell out through the generality of the instruction set.
yep, for the recording.
Yeah.
It was not a deliberate, as you say, it was not a deliberate decision to have a hardware counter. In the paper, if you read it, Bell spends a lot of time talking about there are actually 3 models for a machine. An entirely stack-based machine, which we think of if you've ever looked at how the JVM works, like its underlying model is a stack. There is a one argument, which is loading, like treating a register as a single accumulator, load it, keep adding to it, put the result back. And there is a 2 argument machine, which is add from one register to another. So there are 3 models, like 3 computing models that the PDP could support. And at the time they designed, it was not clear which was actually the success. Like there was a lot of people talking about stack machines because conceptually stack machines are really easy to talk about. They're really easy to reason about, and they have fairly efficient coding. Like you never have to, you have very efficient instruction encoding. This is why the JVM is based on a stack machine, because it's tiny little instructions that say push pop, push to, duplicate, things like that. So the final answer is that it was, yeah, as you said, just something that fell out of the design. They were not prepared to commit to any particular model, like whereas Intel is very much a memory-to-memory architecture. This supported all 3, stack machine, memory-to-memory, and register-to-register.
Cool. A reminder that longer questions, we're going to go to the bar. So yeah. Any question? Okay, you.
Raise your hand if you've used a PDP-11.
I built a simulator.
Sweet. Questions? This side? Okay, going over there.
If you were to take the team that worked on the PDP-11 and drop them into like today's software engineering environment, how would they approach engineering differently or architecting products differently? Or
so there isn't a lot of evidence from the paper that I've written or that I read or the other papers that really highlighted DEC as a particularly kind of innovative hardware design team. Like the section about everything that happened after the PWX project fell apart, and like someone had half a design and they spent all Saturday kind of knocking it up into something that was passable. There isn't a lot really to take away from the way things were designed at DEC. Like you can look at other stories. Like there's a book about the designing of the P6 microprocessor by Robert Caldwell. I think that's his name. Where he goes much more into. We had 3 of us, and this was at Intel, and because of Intel politics, apparently they couldn't have a conference room, so they found one that was locked, and they would just every day just jimmy the card. So everyone else thought that this conference room was locked, and they would just leave them alone for weeks and weeks, and they just whiteboarded, and then had a second phase where they brought on a few more people, and then kind of into the big production phase, which is just the kind of grinded out slugging of commercial engineering. There isn't a lot of evidence about DEC being a particularly enlightened or kind of inspirational workplace. Like there are stories that they had a very kind of you see it, you own it culture. Like there was a story I found once that someone had just joined and he mentioned to a coworker, "Hey, the thing we're doing over there is wrong." He said, "Well, now you've told me about it. You have 2 choices. One, I can fix it, or you can fix it. And if you don't fix it, we'll fire you because you knew about it." So they're very much like you see it, you own it kind of company. But I think the section that talks about like how quickly they were growing and how quickly they were reorganizing kind of says that maybe they were not really in charge of their growth. Yes.
Did you also find it cute that Gordon Bell thinks DEC had an effective and aggressive marketing arm?
I love that line.
Can you repeat the question, please?
So the question was, did I think it was cute that Gordon Bell wondered if the success of the PDP-11 was solely due to the effectiveness of their marketing arm?
DEC are notorious for bad marketing.
Oh.
Yes.
Huh? All right. One more over there.
I just want to answer that one question. I worked for IBM, and I think a lot of it had to do with IBM charging too much for mainframe access time. I really think those students were lining up for that machine because they had to get dollars to use the mainframe.
Awesome. Okay, do you do the last? Okay. Anybody else? All right, let's do the last, and then after the last one, we're going to go to a bar. We probably have a few minutes in here, so just pick up your things at the end. But last question.
Paul.
So first of all, I want to say thank you for a really fabulous talk. That was excellent.
You.
It was just
that means a lot coming
blast
from
the
you.
past. I have a lot of personal history here. I earned a PDP-11 at University College London that I put the first spacecraft experiment on the space shuttle from them. And Gordon Bell, 20 years later, worked for me when I was a senior director at Sun Microsystems. And it was fun because he went to a Vanguard conference and said that he wants work for me, and I felt so honored that he said that. He was actually a consultant. But after that, even 10 years later than that, and more recently, Gordon Bell became a personal friend. And I got to tell you, the character, the inspiration, the brilliance of the man it's off the charts in every dimension, and I aspire to be 1% of what he is. And so, brilliant. The Gordon Bell Fan Club, yes.
This is very much why I wanted to. Thank you. This is very much why I wanted to talk to this paper, because that was abundantly clear in his writing of just how perceptive and how wide his vision was. So yeah, it was. Yeah, I'm in awe of you. Thank you.
Yep. Thank you so much.